One of the most awe-inspiring natural phenomena you may have witnessed is a streak of lightning passing from thunderclouds to the ground on a dark, stormy night. A brilliant flash of lightning can travel nearly 400,000 kilometers per hour, and it can heat the surrounding air to a temperature hotter than the surface of the sun. A single bolt of lightning contains more than a gigawatt of electrical power, enough to supply the energy needs of over 750,000 homes for a day. On a much less dramatic scale, most people can relate to the shock you sometimes get when you touch a doorknob after walking across a carpeted floor on a dry day. A lightning bolt and a carpet shock are both discharges of static electricity. Static electricity is the energy produced by electrical charges at rest. In this lab, we will explore electrostatics, which is the study of static electricity. As always, before beginning any experiment in the laboratory, be sure you are familiar with laboratory safety requirements. For a demonstration of basic lab safety rules, you can watch our video entitled Lab Safety. Some of the effects of static electricity have been known since ancient times. The ancient Greeks discovered that a glass rod rubbed with a piece of silk would attract lightweight things such as dust, feathers, and crumbs of food. The phenomenon of producing a static charge by friction is known as the triboelectric effect. Tribo is the Greek word for rubbing or friction, so triboelectric refers to an electric charge produced by friction. In the 18th century, an American statesman and amateur scientist named Benjamin Franklin made some important discoveries about static electricity. You may have heard about his experiment flying a kite in a thunderstorm, but that was not his most important experiment with static electricity. Probably, his most important experiment with static electricity involved two small spheres made of plant fibers. When he charged a glass rod with a piece of silk and held it near the spheres, the charge from the rod was conducted to the spheres, and the two spheres moved closer to each other. Benjamin Franklin concluded that some invisible electric fluid passed from the rod into the spheres, which caused the charged spheres to be attracted to the glass rod. Benjamin Franklin tried the same experiment with a rubber rod that had been rubbed with a wool cloth. When he held the rod near the spheres moved apart. They were repelled by the charged rubber rod. He concluded that a second kind of invisible electric fluid caused the spheres to be repelled. Benjamin Franklin's conclusion about two kinds of invisible electric fluid was incorrect. Now we know that instead of electric fluid, there are two kinds of invisible particles with opposite electrostatic charges. The electrical charge of a particle at rest is its electrostatic charge. The two kinds of particles with electrostatic charges are protons and electrons. Protons are positively charged particles in the nucleus of every atom. Electrons are negatively charged particles that orbit the nucleus. Since protons and electrons have opposite electrostatic charges, they attract each other. Two protons repel each other because they have the same electrostatic charge. The same is true of two electrons. They repel each other because they have the same electrostatic charge. Most of the time, the atoms on the surface of an object have a neutral electrostatic charge. However, when surface atoms gain additional electrons, a negative electrostatic charge builds up. Likewise, when surface atoms lose electrons, a positive electrostatic charge builds up. A buildup of electrostatic charge can be caused by friction, electrostatic conduction, or electrostatic induction. We can demonstrate the triboelectric effect caused by friction with a rubber rod and wool cloth. Before the rod is charged, the number of protons and electrons in its surface atoms are balanced, so the rubber rod has no electrostatic charge. The uncharged rubber rod neither attracts nor repels these pieces of foam and feathers. When we rub the rod with a wool cloth, friction causes electrons to be transferred from the cloth to the rod. The transfer of electrons causes a negative electrostatic charge to build up on the surface of the rod. Since the rod has become electrostatically charged, it attracts the pieces of foam and feathers. A similar action happens with a glass rod and a silk cloth. Before the rod is charged, the number of protons and electrons in its surface atoms are balanced, so the glass rod has no electrostatic charge. Notice that the uncharged glass rod neither attracts nor repels the pieces of foam and feathers. When we rub the glass rod with a silk cloth, friction causes electrons to be transferred from the rod to the cloth. The transfer of electrons causes a positive charge to build up on the surface of the rod. Keep in mind that the rod has not gained any protons, but it has lost electrons. Since it has lost electrons, it is less negative, which gives it a positive charge. Since the rod has become electrostatically charged, it attracts pieces of foam and feathers. We have seen how a buildup of electrostatic charge can be caused by friction. A buildup of electrostatic charge can also be caused by electrostatic conduction. Electrostatic conduction is the production of an electrostatic charge on an object by direct contact with a charged object. We can demonstrate electrostatic conduction with an electroscope, which is a device that can detect an electrostatic charge. Our electroscope consists of a glass flask that is insulated from outside charges with a rubber stopper. A metal stem is inserted into the flask through the stopper. At the top of the stem is a round electrode. At the opposite end of the stem, inside the flask, a clip holds two thin strips of foil. Let's see what happens when we touch the electrode of the electroscope with a negatively charged rubber rod. Since the rod has more electrons than protons, electrons are conducted to the electrode, which gives the electrode a negative electrostatic charge. The negative electrostatic charge of the rod has been conducted to the electrode. The extra electrons in the electrode are transferred downward through the stem, into the flask, and onto the strips of foil. Now the foil strips have a surplus of electrons, so each strip develops a negative electrostatic charge. Since each strip has the same charge, and like charges repel each other, the two strips diverge. When we move the rubber rod away from the electrode, the strips of foil converge again. The third way that static electricity can be built up on the surface of an object is by electrostatic induction. Electrostatic induction is the redistribution of electrostatic charges in an object when a charged object is brought near it. We can demonstrate electrostatic induction with the electroscope. Notice what happens to the foil strips when a negatively charged rubber rod is moved closer to the electrode. Even though the rod is not touching the electrode, the foil strips diverge. So what is happening? Every charged particle is surrounded by an electric field, which is an invisible sphere of energy that radiates outward from a charged particle. The force of attraction or repulsion of a charged particle acts within its electric field. If an electron enters the electric field of a proton, the energy of the electric field becomes a force of attraction that tries to pull the electron closer to the proton. If another proton enters the electric field of a proton, the energy of the electric field becomes a force of repulsion that tries to push the other proton away. A proton entering the electric field of an electron will be attracted to the electron. Another electron entering the electric field of an electron will be repelled. The electric field strength of a single proton or electron is extremely small and extends only a short distance. But the combined field strength of billions of particles can extend greater distances with greater force. This is how the particles in a charged rod can affect the particles in an electroscope without the rod touching the electrode. When a negatively charged rubber rod is held so that the electrode of an electroscope is within its electric field, the electrons in the electrode are repelled by the charge in the rod. Some electrons move out of the electrode, down the stem of the electroscope, and onto the foil strips. This induces a negative charge on the folds, so they diverge. Electrostatic induction works only while an object is within the electric field of a charged object. When the rod is withdrawn so that the electrode is no longer within the electric field of the rod, electrons return to the electrode, the foil strips lose their charge, and they converge. As we learned previously, a buildup of electrostatic charge can be produced by friction, electrostatic conduction, and electrostatic induction. A device that utilizes all three methods is the Van de Graaff generator. It was invented by American physicist Robert Van de Graaff in 1929. A Van de Graaff generator produces a high-voltage electrostatic charge that collects on a metal sphere or dome. Inside our generator, a rubber belt is stretched between two rollers, a lower roller in the base of the generator and an upper roller in the center of a metal dome at the top of the generator. An electric motor pulls the belt around both rollers. At the lower roller, friction causes electrons to be transferred from the belt to the roller, which leaves the belt positively charged. At the same time, a power supply with a positive charge pulls additional electrons through the lower comb. This increases the positive charge on the belt. The positive charge on the belt is conducted upward until it reaches the upper roller. Electrons from the metal dome that are attracted to the positively charged belt pass through a conductor onto the upper comb and onto the belt. As electrons are transferred from the dome to the belt, a positive charge is induced on the surface of the dome. As the belt continues to turn, the positive charge continues to build up on the dome. Eventually, the electrostatic charge becomes strong enough to overcome the gap between the Van de Graaff generator and a discharge electrode, and an electrostatic discharge jumps from the electrode to the Van de Graaff generator. Our Van de Graaff generator has been charging for several minutes and should be about ready to discharge. When you receive a shock after walking across a carpeted room, the electrostatic discharge could be as much as 35,000 volts. However, a discharge from our Van de Graaff generator may be more than 10 times greater, delivering as much as 400,000 volts. Even though a discharge of this amount may cause some discomfort, it should not cause any permanent injury. This is because the discharge is so quick and because the electric current is less than 0.4 amperes. Earlier, we saw how electrostatic charges can exert a force of attraction or a force of repulsion. The Van de Graaff generator can be used to demonstrate attraction and repulsion of electrostatic charges. You may have noticed how static electricity can sometimes cause your hair to stand on end, especially on a cool, dry day. When your body acquires an electrostatic charge, usually through friction, each strand of hair acquires a positive charge. Since each strand of hair has the same charge, the hairs repel each other, which makes your hair stand on end. If I were to touch the dome of an operating Van de Graaff generator, my hair would stick out from my head. However, we can achieve the same results with these streamers attached to the dome. With the generator switched off, the streamers hang straight down. When the generator is switched on, a positive charge is conducted to the streamers. Since each streamer has the same electrostatic charge, the streamers are repelled, which causes them to stand out from the dome of the generator. When the generator is switched off, the streamers lose their charge and hang down again. Aluminium is a good conductor of an electrostatic charge. So, what do you suppose might happen to this stack of aluminium pans if we stack them on top of the Van de Graaff generator? When the generator is switched on, an electrostatic charge is conducted from the dome of the generator into the pans. As the charge builds, each pan acquires a positive charge, so the pans repel each other and fly off the stack. In this lab, we explored electrostatics. In our next lab, we will investigate electrodynamics. At this time, proceed with the corresponding activities.